This is Chapter 3, Section 2, Introduction to Functions. So we have three really important concepts for this chapter. One is relation, the other is domain, and the other is range. And literally, the very first one, a relation, is probably the easiest definition in all of mathematics, at least as far as memorization goes. So a relation is, this is its definition, and here it is a set. Okay, so a relation is a set. But what types of elements does the set have? It's a set of ordered pairs. So I'm going to give you an example. So I'm going to call this relation R. That's really imaginative. So it's a set. And what types of elements do we have in the set? This is a set that's going to have so few elements in it, I can actually write them out. So each element's going to be separated by a comma, and each element is an ordered pair. So remember, an ordered pair is not a set. It's something quite different. So this is going to be a set of 1, 2, 3, 4 different ordered pairs. It doesn't matter how many ordered pairs the set has, as long as it has at least one, then it's a relation. And that's it. It's just a set of ordered pairs. Now, a lot of our sets will have so many ordered pairs in there that we can't enumerate them all. So this is just called the set list format of a set. But I'll call this relation 1, and I'll call this relation 2. Here is another way to write a set that has so many elements in it, it's impossible to list them all. R2 is the set of, in this case, we would say ordered pairs. Remember, the vertical bar is read as such that y is equal to 2x plus 3. This is actually going to be a linear equation. This is a linear equation, and its graph is going to be a line. So I'm just going to kind of sketch it out here. So if I have my Cartesian coordinate axis, and I'm not going to do this, this is really going to be just a sketch. It's going to be more or less something like this, a line like that. And what this visually tells you, if this is a point x, y on this line that is given by the equation y is equal to 2x plus 3, then that ordered pair xy is in this relation. So there we go. So let's go on. So if this example 2, is a little bit too much for you, just focus on example 1 right now and how easy this particular definition is. A relation is a set of ordered pairs. It doesn't say how many elements it has to be in there, but I think we require at least one. We don't deal with the trivial relation. And this is one example when the elements can actually be enumerated because there's only 4. And down here, I've given another example of a set of a relation whose elements are so numerous they could never be enumerated. They're infinite. So there's an infinite number of ordered pairs in this relation. So we have to write it a different way. Let's go on to the second concept, the domain. So the domain is a word whose meaning depends upon the context. So what's really we're talking about here is we're talking about the domain, and what's understood is of a given relation. So there's no general answer to this. We have to be given a relation. It's also a set. Is the set of all of the x values in each ordered pair that makes up the relation. So let's go back up and let's look at these two relations that I wrote. So let's look at this first relation here. So relation 1. The domain of R1. Well, let's look again. It's a set. So I'm going to write this as a set. And what is in the set? It's the set of all of the x values in each ordered pair. So it's not a set of ordered pairs, but rather the x value of each ordered pair. So we can just simply write them here. Here's the first ordered pair, and its x value is 0. Here's the second ordered pair, and its x value is 1/2. Here's the third ordered pair, and its x value is 1/4. And the fifth ordered pair has an x value of -1. So this is the listing of the domain of R1. Well, let's look at the domain of R2. Again, it's going to be a set, and it's going to be a set of every x value that lies on this line. So here we go. This line extends everywhere. It keeps going in this direction, and it keeps going in this direction forever, as do my x-axis and my y-axis. So if you think about it, if I look at my x value here, so right here is a typical value xy that lies in the relation R2. R2 is given by all of the ordered pairs that lie on this line. If I drop a perpendicular down, I'm going to find an x value that would go into the set of the domain of R2. So that's going to cover an awful lot of space. I hope you can see that starting right here, every x value greater than that point is included. But if I come down to where the line crosses underneath the x-axis, a point xy here corresponds to a point up above on that line. So all of the space forever and ever. So it turns out that the domain of this linear function described by y is equal the sets of ordered pairs xy that make this a true equation happens to be, we can no longer write it in set listing formation, we can write it in interval formation. It goes from minus infinity to infinity. Another way to say the domain of R2 is to say the domain of R2 is the real, meaning real numbers, line. Means all real numbers. Another way to say that is all real numbers. Okay. Now let's look at the range. The range is a similar definition to that of domain. You have to have a given relation in mind. Range of some given relation. Remember, a relation is what? A set of ordered pairs. So the range of a given relation is, what is it? It's a set. That shouldn't be a surprise to you. Of all y values found in the ordered pairs contained, just put of the relation. So let's go up. I'm kind of running out of space. That's okay. I think we can still do this. So let's consider the range. I mean, I'm not running out of space. I have huge digital paper here, but I want you to be able to see this is my first relation and this is my second relation. Just a reminder. The range of R1. Well, we know it's a set. A lot of sets here. And it's the set of y values found in the ordered pairs of R1. So 7 is a y value. Minus 20 is a y value. 21/9 is a y value. And minus 4 is a y value. Suppose I had another element, another ordered pair in R1, and let's just pretend it exists, and it's 3 minus 4. I already have minus 4 in the range of R1, so I would not write minus 4 again, because a set is made up by its elements, and to list an element twice is redundant. It doesn't change the set, so you wouldn't want to list it twice. Now let's go to a pretty simple question. What is the range of R2? So here again is my generic point on the line. So this line right here represents all of the ordered pairs that are in my R2 relation. So how do I find a y value? I come down here and I see and take a perpendicular line down and find out where it hits the y-axis. Down here I go over that way. And since this line extends up slightly, since this line actually has a slope to it, all of my y-axis will be covered. I don't know how to best, this is what I've done in the past. imagine that this is a line. This, of course, this line right here, and you've got a light bulb up here, and it's shining down. Looks like a shower head. Or a UFO. I can't draw people. I'm not going to make any bones of it. So, how much of, I'm talking about the domain now, how much of the x-axis would be shaded? Well, this part up here shades all of this part of the x-axis, and this down here shades the rest. So let's do the same thing. Let's maybe a flashlight or something. I don't even want to try to draw, but it's a light shooting horizontally. So that means this part of the y-axis will be shaded from this light, and this part of the y-axis will be shaded from this light. So the range of this relationship here, is, again, the entire real line. And here is a fact. I'm going to give you a fact. Any linear equation whose graph is not a straight line, horizontal. I don't need the word straight, they're all straight. Whose graph is not a horizontal line, or a vertical line, running out of space, has domain and range minus infinity to infinity. And that's an awful lot of linear equations. So we've already kind of done this, but we're actually ready to do an exercise. And we're going to go ahead and do these, as we'll have it clean. I'll clean my drawing space up. So let's look at the first. Here's my relation. So what's written down in A is a relation, right? It's a set of ordered pairs. So let's find the domain of A. Well, again, it's a set, and what is in the set? It's the set of all first element values. Well, it has 4. There's another 4, but I've already got 4 there. 5, and another 5, but I've already got 5. So it actually turns out to be the set 4, 5. So let's find the range of A. Well, again, it's another set. And now I'm just grabbing the y values. So there's a 1, a -3, a -2, and a 6. So that's the range of A. So that's not so bad. Now let's go on down here, and let's try to answer the same question. And here we have the graph of a relation. A lot of points that have been plotted. And in this case, we want to find the range of B and the domain of B. So we want to find the range of B. So we know it's going to be a set. But let's find what B is equal to. B is a relation. It's a set of ordered pairs. So we'll start right here at 3. The coordinates of this ordered pair, the x value is 3 and the y value is 0. This next point here, the x value is 3, the y value is 1. The x value on this point is 3 and the y value is 2. I think you see what's going on now. And then I have 3, 3 and a 3, 4. But I've not got them all. Down here the x value is still 3, but the y value is minus 1. And 3 minus 4. So here is my end set. So be careful. These are the curly braces that indicate a set. These commas right here indicate different elements in this set. These are not intervals because the context is an ordered pair. This is the coordinates, the xy value of a point. So each one of these is an ordered pair, or a point, if you want to call it that way. It's actually a two-dimensional point because it takes two pieces of information to identify it. And so it has all of the elements are separated by a comma. Guess I need a comma here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements, which correspond to these 9 ordered pairs. 1, 2, these 9 points. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's find its range. I want to talk really before we do it. It's really simple. The range and the domain. So visually this is a point. Algebraically it's an ordered pair. So sometimes we say it's an ordered pair, sometimes we say it's a point, but if I'm talking about the graph of an ordered pair, this is it, the visual thing, that point right there. If I want to talk about where that point resides, then I give its ordered pair coordinates. So let's do the range. So the range of B are all of the y values. So I have a 0, a 1, a 2, a 3, a 4, a minus 1, a minus 2, a minus 3, and minus 4. And what about the domain of B? It's all of the x values. But every x value is 3. So the domain of B is simply one number. The range of B has 9 numbers in it. So now let's look at, all of that is to warm us up to this most fruitful concept in mathematics called the function. So I'm going to give you the technical definition of a function. And then I'm going to give you kind of a visual definition, etc. So here we go. What is this? This is objective 2. A function is a special type of a relation where every element in the domain of the relation is paired with only one element in the range. It's a special type of a function. So, it's a special type of relationship. A function is a relation, but it's a special type of a relation. So what does this down here mean? So I'm going to show you an example of what it means. We can't have a function like this. So I'm going to give an example. So remember, a function is a special type of a relation, so it's going to be a set of ordered pairs. And one ordered pair is going to have 7, 5, and the next ordered pair is going to have 7 minus 1. Why? So this is a perfectly fine relation. So this is okay for a relation, because a relation is really loose. It's just a set of ordered pairs. But a function is a special type of relation. So this is not a function. Why? Because it fails the function test. Because here I have 7 in the domain, and 7 is paired with a 5 and a minus 1. So it's an ordered pair where the domain value 7 is the same in each case, but the range values are different. Whenever you have that, it is not a function. So I just gave you a negative example rather than a positive example. So to recap, this is a relation but not a function. But notice that every function is a relation, because functions are all special types of relations. It's just like every dog is a mammal, but not every mammal is a dog. Dogs are mammals that have special properties. There's a lot of mammals which are not dogs. So let's look at this and let's determine whether the following is a function. So this is definitely a relation. It's a set of ordered pairs. So what am I looking for? So 2 is paired with 5. Minus 2 is paired with 5. And I don't see a minus 2 paired with anything else. A 2 is paired with 7, and there is no 2 paired with anything else. A minus 3 is paired with 5, and minus 3 is not paired with anything else. And 9 is paired with 9, and that's the only thing 9 is paired with. So in example 2a, this is a function. We already know it's a relation. As soon as I say something's a function, I know it's a special type of a relation. But if I just give you a relation, it may not be a function. Now let's look down here and do the visual example. So again, the visual example is probably going to be the best of our examples to look at, because the beauty about graphing is we have literally a visual ability to determine things rather than just figuring out things with the organ of the intellect in our mind. Sometimes we can use our eyes. So I'm literally looking for a value of an ordered pair that matches a domain value with two different range values. And if we look right here, we will find that 0, 3 is an element of this domain, and so is 0 minus 2. So here we have the same domain element paired with two different range elements. So this is not a function. And finally, sometimes it's hard to find it. Let's look at this last one. So C is also a relation, so the question is C a function? Well, we have 3 paired with 3 only appears once, minus 3 only appears as domain element once, and 8 only appears as a domain element once, and 9 only appears as a domain element once. So 3C is also a function. So this leads to, I think that's what we're going to do next. No, we're not. We actually will get a visual test about how to look at the graph of a relation and tell by looking at it if it's a function. So let's go ahead and do number 3. So we're going to be given a relation. So this relation here in 3, our relation is given by the set of ordered pairs x, y, such that y is equal to 2x plus 1. So this is a graph of a linear function. So let's actually graph this line and use that bit of information I told you. Since I know it's the graph of a line, all I have to do is find out if it's the graph of a horizontal or a vertical line. And the trick here, the first thing to try, it doesn't always work, is to do a table of values and choose kitty corner zeros. So here I have y is equal to 2x plus 1. So I've chosen 0, so let's for x. So let's figure out 2 times 0 plus 1. So that gives me y is equal to 1. Now I've chosen 0 for y. So I solve for x. So I move the 1 to the other side. I subtract 1 from both sides. And then I divide by the coefficient of the variable term. And that gives me minus 1/2 is equal to x. So let's plot this really fast. Just kind of eyeball it. You've got to give me a Cartesian plane. So the point 0 and 1. So the x value is 0, so this is my x, and this is my y. So my x value is 0 and my y value is 1. So right there is the point 0, 1. And now I have my x value is minus 1/2, and my y value is 0. So there's my second point. So let's draw a line through them. You don't really have to draw a line through them, but it's clearly not a horizontal or a vertical line, so we already know by that little bit of information that I gave you earlier that the range is the same as the domain. And what is the range in the domain? Minus infinity to infinity. It's the entire real line. So let's look at this one. Is the relation y is equal to x squared a function? I'm going to go ahead and plot this for you using GeoGebra, because the point here is that we just look at it. So what are we looking at here? What are we trying to discover? Well, there it is. It goes on forever and ever. These just keep getting further and further apart. So do I ever have any x value? So let's look at x is equal to 1. Does it ever intersect the graph? Ever again? No. Let's look at x is equal to 2. It intersects the graph right there at 2 and 4. Does it ever intersect the graph again? No. So in this particular case, the relation y is equal to x squared is a function. What about the graph x is equal to y squared? So let's look at that one. No, that's not what I want. So let's go ahead and turn off this one. And now I'm going to put x is equal to y squared. So much easier. So that's in equation 1. And here we can actually easily see this point right here. Let's look at 2. Right there's a point. And right there's a point. Well, that should be 2, but that point has 2 as a value. Ignore this stuff over here because I'm eyeballing it. But right here and right here, if we just follow the line, as a matter of fact, let's just draw the line. I'm messing up all the time. Let's draw a line here. Let's draw a line that goes straight down. And we'll notice this line intersects the graph of x is equal to y squared in 2 different places. So this is actually supposed to be a straight up and down vertical line. I didn't quite do it, but because it intersects the graph in 2 different places, we know that this is the graph of a relation, but the relation itself is not a function. So the graph of y is equal to x squared is a function, but the graph of x is equal to y squared is not. And I just literally gave you what I used, the vertical line test for functions. So the vertical line test for functions is the following. Given the graph of a relation. So we're given the graph of a relation. What's our question? Is that relation a function? If there exists any, that means just one will work, vertical line that intersects the graph of the relation at more than one point, you can think a point is a place, then the relation is not a function. If no such vertical line exists, then the relation is a function. So, some points to remember. We're given the graph of a relation. And then I'm just looking for just one. You can have an infinite number, but all I need is one vertical line that will intersect the graph of the relation at more than one point. If that's the case, I'm done. It's not a relation. If no such vertical line exists, then the relation is a function. So just in case I misspoke there. So given the graph of any relation, all I have to do is find one vertical line that intercepts the graph of the relation at more than one point, then that relation is not a function. If no such vertical line exists, period, then the relation is a function. So it's kind of nice. We have a visual test. We don't have to do any algebra. This is the one question almost every student gets. So these are all graphs of relations. So let's determine which ones are also functions. Can I draw a vertical line that intersects this line here more than once? No. As a matter of fact, by what I said at the very beginning, this is a line with a slope. It's not vertical. It's a line that's not vertical or horizontal. So by what I said before, it is a function. What about here? It's a horizontal line, but it is a function. Sorry. What I told you, so I just said something that was false. What I told you at the very beginning is if the line is not horizontal or vertical, then its domain and range is minus infinity to infinity. I didn't say anything about functions and relations at the very beginning. So now I will tell you what the answer is when it comes to relations and functions. So if a line is not vertical, then it's a function. So here's two prime examples. So clearly this passes the vertical line test because I cannot draw any vertical line that will intersect the blue line more than once. So A is a function. Here's a horizontal line. I cannot draw any vertical line that will intersect it more than once. So it's a function. Now let's come down here and look at the vertical line. Can I draw a vertical line that intersects it more than once? Yeah. I can draw a vertical line right on top of it, and it intersects it at an infinite number of places. So E is not a function. B and A is. So now let's go back to my question about the domain and range. The domain of A is minus infinity to infinity, and so is the range, because it's a line with a slope. It's a line that's not horizontal or vertical. Over here, I have a horizontal line. Its domain is minus infinity to infinity. Imagine the light bulb up here. It would shade all of the x-axis, but its domain is the single point 4. Down here, I have a vertical line. Its domain is the single point 4, but its range, think about a light bulb going this way, it would shade all of the y-axis, is minus infinity to infinity. So now that I've cleared that up, let's look at, this is also the graph of a relation. Is it also a function? Can I draw any vertical line that will intercept it more than one place? No. The closest I could get would be right there and right there, but if I were to zoom in, we will find at most this is a circle, and that would be a tangent line, and it only intersects at one place. And here again we have a no vertical line will intersect this graph more than once. Do I have flame shot? Let's do this. I want to do something really fast. I'm going to use this example. Nope. Where's my, there we go. I'm going to use this example. So, layer. It's going to be somewhere. Where is it? Well, maybe that did not work. There we go. So all I did was just repaste what I wrote, but what I'm going to do is I'm going to rotate it this way. So now what I've done is I've redesignated the axes. It's not perfect, I know. So now this right here is my x-axis, and this here is my y-axis. Here I can clearly draw all kinds of vertical lines right in this area right here, between this area here and this here. Should have used and draw all kinds of lines between this point here and this point here. Still not perfect, but there's all kinds of lines, vertical lines I can draw between there that will intercept the graph of this relation in more than one place. So in this case, not a function. I just wanted another example to give you. So, oh yeah, so now actually good. We're going to determine the domain and range of each of the relations given below. I've already determined the domain and the range of the lines, the horizontal line, the vertical line, and the non-horizontal or non-vertical line. So what would be the range and the domain of this one? So I kind of want to do that again. I want to take a screenshot and copy it in. Okay. So here we're going to have to be careful. What I want to do is we want to find the domain and the range. So the domain has to do with what area of the x-axis would be shaded if I had a light shining up this way and a light up above it shining down. And I can imagine that. I'm just trying to look for visual things. So if we're really, really careful, we will see that if we put right here and go straight down, and right here and go straight down, that the area shaded is going to be the interval. It's hard to know, so we'll just say it's an open interval from 1 to 5. I'm not for sure about the endpoints, but it's an interval that either does or does not contain one or both of its endpoints. So let's just pretend it contains the endpoints, and you would look at it that way. So that is the domain. Remember, the domain is a set, and an interval is the set. Now let's do the same thing for the range. So again, we're going to kind of look right there. We're thinking about light shining in from the left or the right. So here, in this case, our light bulb image is the flashlight or whatever is shining in horizontally. But here it doesn't make any difference. We got it all because it all lies. So this is the y-axis here, and this is the x-axis here, in case you didn't realize. So it looks like it is 3 point, how many? 1, 2, 3, 1, 2, 3, 4, 5. So each one of these is 2. So it looks like the range goes from -1, -1.4 to 3.4, something like that. Don't worry about the decimals. This whole exercise is just a visual exercise. If you can see that it includes this area of the y-axis, that's all that matters. So that's the range. So this is not the domain, but the range. Okay. And for this one here, I'm going to let you think about it. Imagine a light bulb shining this way or down this way. Here I do want to tell you, and this is going to be the same in my math lab, they should put little arrows up here. It's kind of hard to do that when you're using plotting software. That means this goes on forever and ever at a slant. It never changes. We're assuming that it forever keeps slanting away. This forever keeps slanting away. So the domain of D will all of the x-axis, which is right here, will be shaded by a light either shining above, down, or below, up. And if I shine the light from the left or to the right, that light has to be located at infinity, of course. All of the y-axis will be shaded as well. So for D, the domain is the entire real line, -infinity to infinity, and the range is -infinity to infinity. So a challenge, which of the following are true? You should easily be able to answer this one because of the dog and mammal question. Which one is true? Every relation is a function. Every function is a relation. I'm not going to give you the answer. So using function notation. So here I'm going to introduce another concept of a function. A function can be considered to be a mathematical rule. Many times we consider the function to be a machine. It has an input, this machine has inputs, so this is my input, and it has an output. And I'm going to name my machine F. Well, what do the inputs are? The inputs are elements of the domain. And those are always going to be real numbers x. So x is the input. The output is going to be a value of x that is transformed by the rule of the function. So the output is going to be range elements. So I enter in elements from the domain of a given function, and it transforms those values, and it outputs them in the form of x transformed by f. And those are elements of the range. So sometimes I will use this notation to indicate that the function f takes a value of f to a value of f of f. But what is f? F is a rule that can be applied to a real number. So that rule could be take the absolute value of x. Take x, multiply it by 2, and then add 1. Take x and multiply it by itself. So this is a function. So we already know, because it's a function, it's a special type of relation, and that whatever value of x comes in, it's going to go to a single value of y. So this is a function visually. It wouldn't make any sense for the rule to say take x and paint it green, because painting green is not a rule that can be sensibly applied to a real number. Another way to look at it is this way. This is going to emphasize the fact that it is a function. So let's put, so this is this mapping here is my f. This is going to be the domain, and this is going to be the range. And let's put some domain elements in here. It would just be really simple. 0, 3, 21, 117, and minus 5. 3, 2, 8, and 7. Now I'm going to actually erase this f, because you know what it is. So when I draw a line, so f is the mapping. F takes 0 to 2, 3 to 3, 21 to 8, 117 to 7, and 5 to 7. In other words, this is still a function. So what would make it not a function is to try to map 0 to two values. 0 goes to 2 and 0 goes to 8. Can't have that. So in our function notation, we would write f, I don't want that color, we would write f of 0, because is a value, right? It's the value of the transformation of f, what f does to 0. So f of 0 is 2. F of 3 is how f transforms 3. And it transforms it into 3. F of 21 is how the function f transforms the number 21, and it transforms it into 8. And f of 117, f transforms 117 into 7, and it happens to treat minus 5 in the same way it does 117. So this is a function. All of this is a function. As a matter of fact, this right here defines a rule that makes the domain that contains 1, 2, 3, 4, 5 elements into a function whose range contains only 4. So remember, you can have two different elements in the domain of the function mapped to the same range element, but not, as I said, this. You can't have 0 mapped to both 2 and 8, because that would require another line here. F of 0 is equal to 2, and f of 0 is equal to 8. And you can imagine ourselves asking, well, which is it? Is it 2 or is it 8? Well, we're not going to deal with that, and we don't have to worry about it because this is a function. So let's go on. So to denote that y is a function of the variable x, we write y is equal to x of x. Grill this into your head. Every time you see a y and it's in the context of functions, it can be replaced by f of x. So y equals the output value of f of x. So y is the range element. It's what the function f does to the input value x as the output. So now so the dependent variable is y, because the value of y depends on what value of x is fed into the function machine. While x is the independent variable, it doesn't depend on anything. As long as x is in the domain of f, it gets transformed by the function, and y is the value that results in that transformation, and y depends upon the function value that is put in. So x is free to choose, y is determined by f. So now let's do, I think we're getting close to the end. I don't know what I did there. I'm kind of going a little bit slower on these, because those who feel really confident with it, you can just plow forward. Those who don't, I'm giving a lot of visual clues and aids to help this stick. This is my last page. Yeah, this is our last. So we are given the transformation rule. So once you're given f of x is equal to something, you don't have to worry about determining whether it's actually a function. You can assume that it is, because we are declaring it a function by labeling it as such. Now, of course, if some Tom, Dick, or Harry off the street were to come in and say that's a function, and they don't know anything about math, we would want to check just to make sure. But in math, when we say something, f of x, we already know it's a function. So what I want to do is I want to find what that rule, so this is the rule, I want to find how f changes the value of 1. So the input value is 1, and that comes from the domain, and I'm trying to find the range element denoted by y, which is given by the input of f into my function machine. Well, it's really simple. All I do is I take x, the symbol x, and I replace it by the element in the domain for which we say it is. It's 1. So 1 squared minus 3 times 1 plus 1. So that's equal to 7. 1 times 1 is 1. 7 minus 3, that gives me 4 plus 1. So that gives me 5. So f of 1 is equal to 5. Now here is the thing. We've been talking about elements in a relation being ordered pairs, x and y. But now we're looking at special relations, which are functions. So now I can literally use the fact that y is equal to f of x, and all of the elements on the graph of a function have the form x f of x. So that's an important conceptual concept for you later on, that my y is equal to the value of x transformed. In this particular case, I could actually give you more information. You never see it this way because it's too much to write. 7x squared minus 3x plus 1. So whatever value I put in here for x, I have to plug in that x value over here, and the output value is y. So here we have the point 1, f of 1, lies on the graph of f, which is equal to 1, and f of 1 turned out to be 5. So the rest is pretty much, that's all of the conceptual machinery that I need to talk to you about. But let's go ahead and do a few of these. There's nothing really particular here. It just has to, this is the plug and chug part of math. Now this one is E, but I'm going to go ahead and do it. G of x is equal to 8x minus 2. So I want to find G of 1. So all I do is replace x with 1 and perform the operation. Well, 8 times 1 is 8, and 8 minus 2 is 6. So that means 1, G of 1, let me start here. Let me go the transformation. So that means the point xy that's in the graph of this function is equal to x f of x. So I'm given 1 is my x. That should be g of x, sorry, because my function name is g. Many times it is f. G, and what is x? It's 1, which is equal to 1, 6. So the point 1 comma 6 is a point on the graph of g of x. We're going to do B and G and then D and H. That's all we're going to do. These are really simple exercises, and they're worked out in detail in your book. I need to go back a page so I can write down what f is. So let's just do it right here. I'm going to write down f of x is equal to 7x squared minus 3x plus 1. And over here, I'll write that g of x is equal to 8x minus 2. So let's do B. Let's find f of minus 2. Well, again, I just plug in 2. Sorry. I plug in minus 2 squared minus 3 times minus 2. So literally I replace the symbol x by the value here, minus 2. So if there's a minus already there, if that 3 wasn't there and I had just a minus x, you still have to replace the x with a minus 2. It has to bring its minus along with it. So that's 7 minus 2 squared is 4. And minus 3 times minus 2 is plus 6 plus 1. So this is equal to 28 plus 7, which is equal to 35. Let's do g of 0. So again, this means that the point minus 2 and 35, which is equal to minus 2 and f of minus 2, which is equal to x, y, is a point that lies on the graph of f of x is equal to 7x squared minus 3x plus 1. I want to do g of 0. Let's do g of 0. So g of 0 is equal to 8 times 0 minus 2 is equal to minus 2. So that means the point 0, g of 0, is equal to 0 minus 2, lies on the graph of g of x. And then the last one, so I'm gonna erase this. So if you need to write it down, there isn't any real reason to write any of this down. It's all worked out for you in the book, in the ebook. But of course, you have to read it. And some of you have reported to me that you do try to read, and kudos to you. I realize a lot of you don't, and many times the reason for that is you simply don't have time. You're taking other classes, and that's the reason you would rather take it when someone explains it to you and works it out. So what I want to do is the last two, because it always throws people off, but perhaps it shouldn't. So I'm going to find f of b and g of b. But it's really simple. F of b. F of b. Well, when it was f of 1, I just took 1 and replaced it with x and evaluated. B is some number that I don't know. So literally all I do is I replace the symbol x with b, and I'm done. And g of b is the same. That's equal to 8b minus 2. Now there's something you could do over here. You could factor out the greatest common factor and say that's equal to 2 times 4b minus 1. So if you're not convinced that that's true, just use distribution and you're going to get 8b minus 2, which is what I started out with. So that's it for 13.2, Introduction to Functions.